going to be looking at the universal law of gravitation from last class. It's right here on your reference table, Fg equals g m1 m2 over r squared. Notice that Fg is absolute value. This equation will just give you the absolute value, won't return a direction of the force of gravity. That's something you need to be able to figure out on your own. All objects attract, so it's pretty straightforward. All right, so for class 3.8, we're going to be going over a few AP Classroom questions as well as some other questions. So let's start with the multiple choice B, number 21. All right, so give this question a quick read and get an idea of what it's showing. So it's asking about how the gravitational force between A and the planet compares to the gravitational force between B and the planet. So we need to figure out which one is greater, which one's lesser. So what we're going to do is we'll do factor of change. So think about which one we're comparing to which one. So see how it's saying A is larger, A is the same. So what we're going to say is that the force of gravity between B is like our test force of gravity field, the one we're not changing. Okay. So we need to figure out the force of gravity on A. Remember, we're going to use our universal law of gravitation. So that's going to be Fg equals g m1 m2 over r squared. So the force of gravity that A feels compared to B, well, G is not going to change, so we put in a 1. Okay. Now, as far as M1 and M2 goes, M1 is going to be the planet, M2 will be A or B in their respective cases. It doesn't matter what you make M1 and M2. I just like to make the planet M1 to stay consistent. So in the case of the force of gravity between A and the planet, in the case the force of gravity between B and the planet, you will notice that the planet's mass does not change. So we put in a 1 there for M1. Now, how does the mass change from B to A? Because B is like our original case. So by what factor did the mass change B to A? You'll notice here it changed by a factor of 2. It's twice as big. Now, how did R change from B to A? Well, it looks like B is 2R away and A is only an R away. So when you went from B to A, by what factor did R change? It's half as big. And don't forget to square that. Multiplying this out, you get 2 over 1/4 which gives you 8. So it's going to be 8 times as big. FGA equals 8 FGB. Now, we actually did the math here. You don't even have to do the math. FGA is larger because satellite A is twice the mass and half the distance. We showed it's 8 times larger. Another way to do it, because we didn't quite need the factor of change, you could have just done FGA and actually put the values in. G, M, 2M, that's the mass of A, and R squared, that's a bad R squared, versus FGB equals G, M, little m, because it's not 2m anymore. And this is going to be 2R that whole thing squared. And it should be pretty easy to see that FGA is bigger than FGB. But it's nice to quantify it too and show that it's 8 times bigger. So let's look at number 8. This is probably one of the hardest questions they could possibly ask on this topic. So give it a quick read. Drawing the question out could help, but this is probably the hardest question they could ask for this sort of topic. So notice here how they say the force of gravity between x and z is F naught. X being this one on the left, z being this one on the right. That is F naught. What we need to do is find the net force acting on y in terms of F naught. That could be a little bit confusing. So you should notice that there are 2 forces of gravity acting on y. It's feeling a force of gravity from x to the left and a force of gravity from z to the right. Those 2 things are pulling it in opposite directions. So that can be a good way to just get started to kind of sketch this out. So if this is my planet Y, I have the force between y and z pulling it to the right, and the force between x and y pulling it to the left. I don't know which one's bigger or lesser yet, so we'll just leave it for now. So we need to first find the force between x and y in terms of F naught. So let's start by writing Fx, y, equals, and we're going to use factor of change here, so g m1 m2 over r squared. G doesn't change, so we put in a 1. And we'll call y mass 1. That's not changing either. So what we have to think about now is the case of we're comparing constantly to the force between x and z. So the force between x and z has a mass of m naught and 9 m naught. So what we'll notice here is that now we need the force between x and y. And actually, I think I misspoke before. We're going to do this a little bit differently. Okay? Let me just erase this for a moment. G is still not changing, of course. So in the original case with F naught, the masses are m naught and 9 m naught. Now they're m naught and 4 m naught. So m naught is not changing. So we'll make that m1. But m2 is changing. It's going from 9 m naught to 4 m naught. So by what factor is it changing? It's 4/9. So you can see already that the fractions are going to be a little tricky here. And how's the distance changing? Well, from x, between x and z, the distance is 3r. Between x, that's our F naught case, right? So that's 3r. Between x and y, it's simply r. So that's 1/3 is far apart. So Fxy equals, you can do the math here, but I think this comes out to be 4. 4 what? 4 times F naught. So this is 4 F naught to the left. Redo that one. That one's a little bit tricky, but hopefully when we do Fyz, it'll be a little bit easier. So of course, big G isn't changing, so we make that a 1. So again, our original case was m naught and 9 m naught. Now between y and z, it's 4 m naught and 9 m naught. One of the masses is not changing, and the other one is being quadrupled. So one of the masses is not changing. The other one is being quadrupled. The one that's not changing is m naught. The one that is changing is m naught to 4 m naught. How's the distance changing? Well, the original case, again, m naught to 9 m naught is a distance of 3r. From y to z, it's only 2r, so it's 2/3. And don't forget to square that. So let's see how this works out. Fyz equals 4 over 4/9. So this comes out to be 9 F naught. So the sum of the forces is equal to 9 F naught plus negative 4 F naught, because it's going to the left. So it's 5 F naught to the right. There it is. This is a really tough question. Just make sure you go over it again. Try to do it on your own from scratch. This is as hard as it could possibly get for this sort of question. All right, so we're sticking with these factor of change, or we're not doing factor of change now, we're sticking with these force of gravity questions. We have a 50 kilogram object, and we'll call it object A, and a 100 kilogram object that are 10 meters apart. The question is, where should a 10 kilogram object, we'll call it object C, be placed such that the net force is 0? And also, where is the gravitational force the greatest? So let's just sketch out a quick little picture here. I'm going to kind of answer these together, A and B. Here's object A, and here's object B. Okay, this is 100 kilograms. This is 50 kilograms. If I were to put object C directly between the two, how would the forces compare between A and C and between B and C? Remember, the distances here are the same. So thinking about Newton's law of gravitation, our values are the same between A and C and B and C. So the only difference then is the masses. B has twice the mass that A has. So there would be a greater force pulling this way than pulling this way. It would actually be twice as big. So we know that it can't be placed directly between the two. What if I move it a little bit to the left? If I move it a little bit to the left, the force between C and B is going to get smaller because the distance is greater. But the force between A and C is going to get bigger because the distance is smaller. So I'll just say it one more time. The force between B and C is going to get smaller because the distance between them got greater. The masses didn't change. The force between A and C is going to get bigger because the distance between them got smaller. So if our halfway point is right here, we know it's got to be closer to A than B. The question is, where exactly does it have to be placed? Okay, I'll start going through the math, and you can maybe finish the math on your own. We'll see how far with it we get. So we know the distance between A and B is 10. That's really important. I'm going to call the location for the net force to be 0. I'll call this location X. Okay, location X. And I'll call this, we know, 10 meters. All right, so I want to find where the net force is 0. So that means that the force of A on B and the force of A on C and the force of B on C are equal in magnitude, opposite in direction. So I need to find where FAB, AC, keep making mistakes there, equals FBC. So the force between A and C is going to be G, mass of A, times the mass of C, all over this distance here. What we're going to call that distance is x. Okay, we've defined that distance as x. X will ultimately be our answer. Like, where does it have to be placed? FBC is going to be G, mass of B, mass of C. Now, what would we call the distance between B and C in terms of x? It would be 10 minus x squared. A couple things cancel out here. G goes away. MC goes away. Notice that the mass of C doesn't really matter. Now, to finish this one up, you can just solve for x. It's not exactly easy to solve for, but now we know the mass of A is 50 over x squared equals 100 over 10 minus x squared. Now you can do the whole FOIL method here. I'm not going to get into that, but you can actually solve this if you'd like. You can FOIL, cross multiply, and get your answer that way. Generally, you wouldn't need to do that, but I think it's really good algebraic practice to try that out. Now, where would the gravitational force be the greatest? So if we put it anywhere between A and B, the forces of gravity are going to be in opposite directions. So if we want the greatest force of gravity, if A is here and B is here, where can I place C such that the forces of gravity are helping one another? Again, if I put it between A and B, the forces of gravity are going to be pulling in opposite directions. Well, think about this. If I place it here, the forces of gravity are both going to be pulling to the right. If I place it here, the forces of gravity are both going to be pulling to the left. So anywhere outside of A and B, the forces of gravity will now be helping each other. Therefore, that's where you would get the greatest force of gravity. Okay, now you might have to assess on a multiple choice question which one or which position would give you a greater force of gravity, to the left of A or to the left of B. But you know, to the left of A or to the right of B, but you know it's going to be outside those two, because again, when you're to the left or to the right of A and B here, the forces of gravity help one another. So this one says, calculate the force of gravity, the weight you feel while standing on the surface of the Earth. All right. So if you're on the surface of the Earth, we'll draw the Earth here. We'll make it green. This is you here on the surface of the Earth. Now, a couple really important things here. When we find the force of gravity, we have to have the mass of the two objects, so you and the Earth. The other thing, though, you need is the distance between objects' centers. Okay? So the distance from your center to the center of the Earth is basically just the radius of the Earth. We would also need the mass of the Earth for this question. Okay, those two are in the Regents reference table. We'll actually use the Regents reference table today just to get a number here. But realize on the AP exam, you probably wouldn't need to do this part. They might just give you the force of gravity. But it's nice to calculate, see where this comes from. So the force of gravity, your weight on Earth's surface, and again, this is on Earth's surface. If you're above Earth's surface, RE is going to change values, right? So Fg is equal to G m1 m2 over r squared. Fg is equal to 6.67 times 10 to the negative 11. M1 and M2 are U in the Earth. I'll just make up a mass for you. We'll make it 70 kilograms. And the Earth's mass, according to the Regents reference table, is 5.98 times 10 to the 24. All over. Now, R is the distance from your center to Earth's center, which is going to be about the radius of Earth. So that's 6.37 times 10 to the 6th. And don't forget to square that bottom number. All right, so throw that all in your calculator. And let me know what you get. I'm going to get a slightly different number here because I don't have my scientific calculator, but it'll be close enough. You use my number or yours, it doesn't really matter. You should get about 686 newtons. Something close to that. You're not going to get the exact number because, again, I kind of just rounded mine. So that's your weight on Earth. We'll get into other ways to do that later on, but we'll leave it there for now. So the mass of Mars is one tenth times that of Earth, and the diameter of Mars is 1/2 that of Earth. What is the force of gravity you would feel on the surface of Mars? Now, I could put in all new numbers here, but that's not what this activity is about. It's about using our factor of change method. So let's call this Fg m for Mars. So let's go through. Is G changing? No, it's a 1. Is M1 changing? We called M1 your mass here. So is your mass changing? No, it is not. Your mass does not change from planet to planet. How about M2? Is the mass of Mars changing? It is. Are the planets changing? By what factor? It's 1/10. Over r squared. Now, is the radius changing? Well, the diameter is changing, and the diameter is linearly proportional to radius. So if the diameter is half, the radius is half. So that's half as big. Don't forget to square that. So what you end up getting here is 0.4. So it's 0.4 times the original force of gravity. So 0.4 times 686 newtons equals 274 about newtons. So that would be your weight, the force of gravity you feel on Mars. We use weight and force of gravity kind of synonymously. So we have a newly discovered planet now, and now we're looking at the planet's density. So there's one more step involved here. The planet's density is 2/3 the density of Earth. That little p is a rho. It's supposed to be a rho for density. So it's 2/3 the density of Earth, so it's less dense, but it's bigger. Its radius is bigger. Okay? So we want to find the force of gravity you would feel on that new planet. So we'll call this planet, I don't know, just Fg prime. So again, big G doesn't change. Your mass doesn't change. But the mass of the planet does change. Okay? We'll get to that in a second. And the radius is going to be twice as big, so we put in a 2. Now, how does the mass of this new planet change? So, we have an equation for mass that you might remember from chemistry. Mass equals density times volume. So, rho times volume. The density is changing here. So, our new mass, m prime, is going to be 2/3 of the original density. So, we're using factor of change again. And our volume formula. Our volume formula is going to be 4/3 pi r cubed. So 4/3. Actually, let me go back a step. So mass equals rho times 4/3 pi r cubed. Now we got to think about how each of these things are changing. For m prime, rho is changing. Excuse me. It's 2/3 is big. 4/3 is not changing. Pi is not changing, but r is changing. R is going to be twice as big, and that's cubed. So it's a huge difference. So m prime is going to be 2/3 times 8. So that's going to be 16/3. Hope I got that right. I may have made a mistake here. If I did, just make sure you pick up on that mistake and fix it in your own work. So the mass is going to be 16/3 of the original mass. So yes, it's going to be less dense. So you might think the mass is going down, but it's so much bigger. So there's way more mass. So Fg prime is equal to 4/3. So 4/3 times 686 is equal to I made a mistake there. About 915 newtons. All right, so those density ones are pretty tough, but if you follow that method I just showed you there, it just becomes a factor of change question kind of off to the side that you don't have to plug your answer into the original.